And then what I'll do is I'll give you the link to get the recording of this. But next week, we will be able to do it through the CSU, system.
Yeah.
Good.
Okay.
Almost everybody's is joined. We have 20.
Yeah, let's see. There are quite a few familiar faces. Rafael, I think Rafael is here. Rafael,
Yeah, I think he's here. I saw his name
and,
right here.
and yeah, Dr. Yeah, hey. Hi, Rafael.
Hello, Rafael. Nice to see you.
Yeah.
Glad to see you.
Are you in Sweden?
Okay.
Yes, we are still in Europe temporarily for a few more weeks.
Okay. Okay, good. Okay, let's start. I'm going to share my window with you. And okay. Oh, there's still some people, even though many people joining at the last minute. Okay. Can you see my?
Yeah, we can see your desktop.
Okay. Me. All right.
Yeah, we can see that.
Okay. I hope you can see the slides. So 38 participants. Welcome. Welcome to this informal talks about discrete time systems. We are going to be making emphasis on nonlinear discrete time systems, especially some structural facts about that class of systems. And we will start with the simplest case. That would be single input, single output, nonlinear discrete time systems. And the structural aspects of these somehow can parallel to a certain extent the same structural aspects that we have in continuous time nonlinear systems. And the idea here is to give you some fundamental facts that will allow us to disembark in two important issues. One of them is difference flatness, and the second one is how to apply these structural aspects to active disturbance rejection control. So in a sense, this is pretty much a parallel to nonlinear continuous time systems. And this is what we plan for the next few talks. So this is more or less the outline of what I call the first lecture, but it will take 2 or 3 weeks to complete all the material here. And from there, we will continue. I keep admitting people, and sorry.
No problem.
Okay.
48 already.
So one of the fundamental issues that we want to tackle is how all these structural aspects of nonlinear systems work out for native discrete time systems. What we understand by native discrete time systems are systems which do not necessarily come from a sampling process, but they are naturally discrete time because of the, let's say, quote unquote, physics of the problem. And This kind of systems is natural in many technological areas and also in some social areas. So in a sense, what we want to do is to make available the tools of active disturbance rejection control and also the tools of difference flatness to that class of systems. Of course, being quite biased towards engineering problems, important problems will also be represented by physically sound systems, systems which are naturally continuous, but that require some sampling before attempting some kind of digital solution of the control problems that can be defined on them. So just to concentrate on what we're going to be doing first, we will have a nonlinear dynamics, which is controlled by some control action, which we call U. And we will assume that U is a scalar function, probably a scalar function of the state, a scalar function of the states, all the outputs, and probably influenced by uncertainty due to the dynamics of the system, although in this case, we're not specifically taking into account the presence of disturbances. We will do so in due time. So at the beginning, we are going to treat the clean class of systems in which there is no disturbances. To explore the structural aspects, we have a state equation, which is constituted by a nonlinear map. This nonlinear map takes states and current control inputs to produce the next state. The set of points in Rn where this function can take values, where the state function can take values, is supposed to be a sufficiently large open set of Rn. So X is a vector in Rn at each instant of time. Our control is scalar, and the next state function is represented by this nonlinear function psi. And we have an output as a reflection of what's going on in the state space. We can measure or we can observe some nonlinear functions of the state, which in general might take values in a p-dimensional space, a Cartesian space, and or Euclidean space, and y, script y, will be a large open set of that space. So in general, we will have a number of inputs and a number of outputs, but pretty soon we are going to concentrate on the case of single input, single output. So the general formulation, this is what we have. We have two nonlinear maps, a state map and an output map. And with this, we will try to attempt in full generality to obtain the most essential properties of those systems. For instance, an economic system of two states and two inputs can be represented as something like this. It's a nonlinear function that economists deduce by some of the laws of the government functioning and people being agents of that economy. So we have, let's say, a very simplified model of an economic system in which X1 and X2 represent capital stock in the private and the government sectors, for instance. And these nonlinear functions are either well known or they are identified as time goes on from charts and graphs that economists gather around from information of the economy. So this is a typical nonlinear system in which we have control actions and we have states that evolve according to a nonlinear map, which is control dependent. So in this particular case, we have a two-dimensional state space with two control inputs that act independently on the economy, and we will have a control objective, which is to regulate the economy in some healthy way, so that things happen or objectives are achieved in the succession of economic terms over time. So that class of systems we call native systems, because they don't come from a sampling process on a continuous system. They come naturally as a result of applying laws of behavior, in this case of economic systems. And for instance, another source of discrete time systems, of course, is the discretization of continuous time systems. And in this case, we can consider, let's say, a linear system, and that linear system is characterized by a continuous time system. If we want to sample that system under the assumption that our controls are piecewise constant, then naturally we are interested in obtaining the value of the state and the outputs at the end of those sampling intervals in a precise manner. Given that the system represents a physical system that cannot be, its nature cannot be, changed drastically to evolve differently than what it's doing. So in a source of those models would be something like this. In this case, we have a linear system, but pretty soon we will try to see how to discretize a nonlinear system. So if under the assumption that the system is piecewise, the control is piecewise constant, we can attempt to obtain an exact formula for the evolution of the state and the reflected values on the output space of those states, so that we can have a discrete model that we can use to do design or analysis. And then our decisions will have to be implemented on the continuous time system, which corresponds to the physical reality. So in that sense, we can use the variations of constants formula, in which we assume that we have a given current state, that we have applied a piecewise constant set of control inputs, and therefore we're producing a new state at every sampling instant. So the variation of constants formula will take x at the sampling time kt as the initial state. It will propagate that state through the system structure, which in this case is just the state transition matrix, and will adjoin to that the influence of our control actions, which are piecewise constant, and they are acting through a convolution integral to complete the next value of the state. And of course, the output will be a reflection through a linear map C of that current state. Using that formula, we can easily simplify all these expressions so that we can obtain a map that relates the current state and the given control input to the next state. And by doing that, we just simply simplify the exponents of the exponential matrix, and we obtain, by means of a simple change of variables in the integration operation depicted here, we obtain the sum of two terms. One of them is linearly acting or acted upon by a matrix, which is just this integral, which will become a constant because its time variation is completely integrated between 0 and t, equivalent to this integration domain that can be modified, given that A and B are time invariant, can be modified into a simple integral like this. So we obtain a next state map, which takes the current state and the piecewise control inputs to conform the sum of these two terms, my actions, the influence of the actual state on the next state, and the influence of my actions on the next state. So we have still a linear system characterized by two linear maps, the presence of the control and the actual state generating the next state, and the output being just a reflection of the current state. So this is a source of discretization. We would have two maps, F and G, which can be computed from the corresponding maps in the continuous time system, and we obtain an exact model. Given that the control inputs are piecewise constant, we have an exact model of the evolution of the sample state at each time moment from an initial time to a final time. So this is a source of examples, the kind of linear systems that you can exactly sample. And the question would be, okay, if this gives me a reliable model, quite precise, of a system that is evolving in a discrete time setting with piecewise continuous controls, can I do something similar for nonlinear systems? And that's the objective now. If I had a nonlinear system, in its most elementary form, it would be an n-dimensional nonlinear system defined by two vector fields and a scalar control input, let's say. This nonlinear system, could we discretize this nonlinear system in an exact form? And for that, we will just have to recall some few elementary facts from calculus in n dimensions, which are just elementary tools from differential geometry, but really it's just calculus in n dimensions, such as defining what we mean by a vector field or the directional derivative of a scalar function in the direction of a vector field. So we have a nonlinear system. This nonlinear system is continuous. And let's assume that U is piecewise constant, much as in the previous example. Can we obtain an exact map giving me the next value of the state at the sampling instant in terms of the current state and in terms of the provided control input that I designed somehow to modify the behavior of the system and to make it evolve towards a desired goal? This is the typical situation in almost any system, the physical system, in which nonlinearities have to be taken into account. So in this class of systems, F and G are vector functions. They are functions of the state, and they are represented as vectors in n dimensions. Each component of this vector is a nonlinear function. And we will assume that we can take derivatives of this nonlinear function. So the class of functions that we will be using is the class of analytic functions. They are very convenient functions because they have isolated zeros and they admit an expansion in Taylor series form, so that some genericity is gained by considering analytic functions. They are zero only at discrete points of time or an isolated roots, and if they are zero on an open set in the defining space, then if they are zero on this open set, they will be zero everywhere. So at any point in the space, we will have something of this analytic function, and that gives genericity to the treatment. That means that's a technical reason why this is important. The analytic function will be present everywhere in the space where it is defined. So this vector of analytic functions admits a representation in the form of a differential operator, in the sense that each component is labeled by a symbol. We will consider this only as a symbol. This symbol means that in the ith dimension, the vector f has component f sub I. And the entirety of the vector can be represented as this sum of nonlinear analytic functions, which are each one of them labeled by the position that it occupies in this vector. So we say that this vector is an element in the tangent space. What we mean by that is that whatever we're considering our system, there will be a sort of a surface where it evolves. Some systems, some nonlinear systems evolve in spheres, or in a torus, or in some manifold, in some surface of the n-dimensional space. Well, those are typical behaviors of nonlinear systems. We cannot constrain the class of systems to Euclidean spaces with Cartesian coordinates, because then the class of systems might become very limited. But of course, a good bunch of examples will come from Rn. And therefore, in Rn, each point will have associated to that point certain tangent space. And that tangent space is a copy of the n-dimensional space that is centered around a particular point x. And that tangent space is the home of vectors. So vectors exist, these vector fields exist at each point of the space where we're defining the states, and they represent a direction and a magnitude around that point. And that direction is given by the components of this vector, and the magnitude is just the magnitude of this vector. So these vector fields give us the idea of something moving in some direction with some velocity. Well, what will be moving in some direction with some velocity is the state itself. So f, if there was no control input, f would represent the velocity at each point of the variation of x. So it gives you the idea of that x is constituted by points that are moving on the space where x is defined. And the space where x is defined can be a Cartesian space, an Euclidean space, or can also be a sphere or a manifold, which is sufficiently smooth. It doesn't have any discontinuities and things of that sort. So the nice way to represent differential equations is to represent them by the differential, by vector fields, because these vector fields give you the idea of a motion in the state space, a flow of the space starting from some initial state and moving along the direction and the magnitude of this field. And this direction, of course, is a function of x itself, so it will be changing as we move on. And G is another vector field that's modulated by the control input and allows you to change the direction in the right-hand side at each point. And in this manner, x will evolve in a controlled manner. So most of the properties of nonlinear systems of this sort will be synthesized by two vector fields, f and g, and u will be our design tool. We will have to design u so that as to make that f plus uu does something that we would like the system to do. So this is just notation, and with this notation, we will be able to obtain things like directional derivatives. H is the output function, let's say, takes values in R. The components of H are also analytic functions. And the directional derivative of this scalar function with respect to this vector, that means the variation of this scalar function along the direction represented by f, will be called the directional derivative, and that will be computed as a scalar quantity, which is the inner product of a row vector given by the gradient of that scalar function with respect to the state, multiplied by the vector field. So LFH is the directional derivative of H in the direction of F. That is the gradient of H times F. which in component-wise form will be just the product of each one of the derivatives of H with respect to each component in X, multiplied by the corresponding component of the vector field. So this sum is the sum of scalar functions and will produce a scalar value of LFH. The directional derivative will tell me how much the function H, which is a scalar function, will be varying in the direction of F. And that directional derivative will be very useful, and this notation will be very useful to obtain properties of the nonlinear system. And in particular, we're interested in exactly discretizing this nonlinear system when U is piecewise constant. This is our objective for the moment. And so that we can have another source of examples in which this exact discretization of this nonlinear system gives us a model which conforms to the adopted model at the beginning of these slides. And of course, this directional derivative has a number of interesting and very comfortable properties in the sense that they are linear maps. They take scalar valued analytic functions defined on the state space and produces as a result another scalar analytic function of the state space. So the class of functions where this map or this operator acts preserves the nature of the mapped element in that space. So h of x is a scalar, and LF of h is also a scalar. And what some of the properties are very nice. For instance, it's a linear map in the sense that if you have a multiple of the vector field f, a scalar multiple of the vector field f, no matter if that multiple is a function of the point in, or as a function of the state or the point where I'm considering this directional derivative, that function, that scalar function, permeates the operator in the sense that it becomes a proportionality factor on the operator itself. So anything that is scalarly multiplying f, even if it's a function of the state, will emerge from that operator multiplying the entire operator. This is a linearity property which is very convenient for the manipulation of these maps. The other property is that the operator is linear with respect to the sum of vector fields. So if f and g are two vector fields, the directional derivative operator will be linear with respect to the sum of those vector fields. So having two vector fields in the tangent space, L of f plus g is simply L of f plus L of g. Those are two very convenient properties because it allows one to manipulate with certain comfort the nonlinear expressions while simplifying enormously the calculations. And of course, if we're dealing with our particular system controlled by these two fields f and g with a structure that we call affining the control input, in the sense that the scalar control input is only acting on one of these fields, the operator on this vector field constituted by the sum of f plus g modulated by u is linear in f, g, and u. Therefore, we have this expression, and so whenever we want to find out how a scalar function is varying along the solutions of the nonlinear system, that operation is easily done by means of this. Some things are appearing on my screen that I'm not doing. Like, is this somebody doing it? Okay. So the directional derivative of, let's say, the scalar function representing the output map along the control vector field F plus GU is linear in F, linear in G, and U comes out to be a factor that can be multiplied by the scalar directional derivative of H with respect to the vector field G. F will be called the drift vector field, and G will be called the control vector field. So this first directional derivative, as you see, is very easy to compute without even writing the differential calculus notation. But we will have to do that sometime in order to clarify what this means in terms of normal calculus in Rn. So remember, our objective is to discretize in an exact manner that nonlinear system. We can extend this operator, which so far has been acting on scalar functions. We can extend it to vector functions. So LF does not have to be constrained to act on scalar functions of the state. It can also act on vector functions of the state. If you have a vector phi which has n components, say phi 1 all the way to phi n in n dimensions, we can stack up all those directional derivatives and define what we mean by the directional derivative of a vector with respect to the vector field f. So this is, in a sense, derivative of a vector in the direction of another vector. And what it comes out to be is simply the distribution of the directional derivative operator along the components of the vector function phi. So each one of the components of this new vector will be a directional derivative in the direction of f of the particular component of the function, of the vector function phi. So in this manner, we can extend the definition of directional derivative to vectors. And as an operator, you see that this extension takes vectors into vectors. And that's why it's called an operator, because it respects the nature of the element that is acting upon and reproduces the same nature in the space of images of that operator. So the directional derivative of a vector function in the direction of a vector f is just the collection of directional derivatives of the scalar components of the vector function in the direction of f. And we will denote this simply by LF of phi, where we know that phi will be clear from the context that phi will be a vector function. In particular, we're interested in applying this extended vector directional derivative of vectors to a particular vector function. Let's suppose we have the identity function in the sense that phi of x is just x. That's the most elementary kind of vector function that we can think of. Well, it turns out that if phi of x is just x, we can take the directional derivative of the components of x along the direction f, the fixed direction f, which is also a function of f. So when we have this and we apply the definition, we will have the gradient of the vector function with respect to x. This is a matrix now. This is the directional, this is the partial derivative of a vector function with respect to the vector of states. Notationally, we prefer to put x transpose here because you see each one of these elements is generating a row vector multiplied by a column vector. So the product is a scalar. But since each one of these is a row vector, this is a collection of row vectors acting on the same vector field F. So this is a matrix. This is a collection of rows, each one of them representing the gradient of the component of phi along the state X. And for that, we just use the transpose notation to denote that each one of the elements in this object is a row vector, and the collection of row vectors is acting on a vector that gives you, as a result, another vector. So if phi of x is x, what we have to do, applying this definition here, is to have the gradient of x with respect to itself in a transposed manner. No doubt this is the identity matrix. So when we use a particular vector function, which is just a state, LF of x is simply fx. So this vector is just f. So a nice way to write the vector function f, or the vector field f, is just as LF of x. And that will be helpful in the notation in order to do some calculations that will follow in the discretization of nonlinear systems, which are affine in the control input. So if we have any other vector function, let's call it z, which is a function of x, the directional derivative of z in the direction of the velocity of x, remember that x dot is just f plus gu. So this is actually the directional derivative of any function z, which is a vector function, in the direction of the velocity emerging from the point x and being adopted by the vector x. That velocity is just x dot. It's just the velocity of the state. So that will give us a matrix, which is the gradient of each component of z ordered as a matrix in a set of row vectors that will be multiplied by this column vector, giving us the product of a matrix times a column vector that gives us, again, a column vector. And this operation will be linear, so we will have directional derivative of that vector function with respect to f, and we will have the modulated part of the control acting on that matrix representing the gradients of z projected onto G. So in this manner, we extend the operation LF to vector functions, and that will allow us to immediately, by means of using this very simple function, to obtain an expansion of the solution of the differential equation, which is controlled by piecewise constant inputs, and see if we can discretize that exactly. So before doing that, maybe LF, as before, we can iterate LF as many times as we want on scalar functions and also on vectors, given that the operation LF on scalars produces scalars. The iteration of an operation already taken with L of f will again be a scalar function, and so on. So we can iterate as many times as we want those directional derivatives of scalar functions, which are just analytic functions that map the state space into the reals. The iteration of those directional derivatives can be denoted by a symbol like this. And specifically, and just to see that sometimes we have to do the actual calculation in Rn, the directional derivative of an already taken directional derivative with respect to the same vector would be the directional derivative of the scalar function that will again be scalar. But this is the gradient of x multiplied by f. And the directional derivative along f of this scalar function will be, again, the partial derivative of all these functions with respect to s multiplied by f. And therefore, we have this, in this simple iteration, we have concealed this more or less complex computation. This computation will have to take the partial derivative of this product of vectors. This is a row vector, this is a column vector. And the result of this differentiation will be multiplied by f. So we have two terms. In these two terms involve the transpose of f, the Hessian of h, and f again to produce a scalar. This triple product is a product of a row vector, is a matrix, and a column vector. This triple product will give you scalar. And that would represent the derivative of the first factor with times the second. Only that operation has to be agreeable with the fact that the whole thing will be a scalar. So the only way to represent this derivative of the first times the second is through the transpose of that first term. And that transpose times f gives you a scalar again. And the first one times the derivative of the second gives you a matrix in this entry. And this is a row vector times a matrix gives you a row vector times a column vector gives you a scalar. So in order to simplify the notation, we'll just put the iteration of f on f is LF square of h. And as you can see, it represents quite a number of computations in the state space. Suppose that the X is 10-dimensional, then we're talking about 10-dimensional matrix here, a 10-dimensional matrix here. It might not be a simple task, but we can simplify, and not only notationally, but also the operations that are involved that we can rely on a computer to do by means of some algebraic manipulator, that LF square is just an entity in itself that represents all this, and we don't have to remember that. We can program this to make this computation whenever we need it. So in general, we can iterate this directional derivative on the scalar functions as many times as we want. If we have an integer number of times that we want to iterate the directional derivative operation on a scalar function f, h, that would be simply the application of the directional derivative to the previously found operation, starting from the fact that no directional derivative simply leaves the function as it is. So with these two formulas, we have a recursion that allows us to compute any directional derivative of an integer order applied on a scalar function along a vector field f. And this will pop up in a few minutes in the next slides in order to compute an expansion that we need in order to find the exact solution of the nonlinear system when we sample the system, given that the inputs are piecewise constant. So with this in mind, we concentrate on the form that this iterative procedure will have on the scalar functions. Let's say let's compute along the solutions of the system. This only represents x dot, remember, so it's a vector in Rn. So the second iteration of the scalar function h with respect to the vector field resulting from the right-hand side of the system dynamics will be the iteration of that directional derivative of the already taken first directional derivative. And when you do that, you see you will have to apply, because of the linearity of f and g, because of that linearity, we can apply this operation first on f to the sum, and then apply the operation of directional derivative with respect to g to the same sum, and obtain the sum of those four terms. And those four terms will give you something very interesting. And what's interesting is that you will have a polynomial in U of order 2 when you do this iteration of the output function along the vector field f plus gu. When you do that 2 times, you have a polynomial of second degree in U. And that polynomial has coefficients which are functions of the state space, but it's a clean polynomial in U. So if we can do this for scalar functions, we can do that for vector functions. And that iteration of L, the directional derivative of f on vector functions, will produce matrices multiplied by vector fields, which give you vector fields again, and therefore we can reiterate the operation. And LF squared simply means the directional derivative of a vector that already contains directional derivatives of each of the components of the nonlinear function C, which is a function of the state. So it's very simple to do that and to reiterate the Lie derivative operation in terms of a simple function x. Instead of any nonlinear function C of x, we can try that on x. And again, we obtain this nice polynomial with directional derivatives of f and g with respect to f and g. And that polynomial has vector coefficients, which are nonlinear functions of the state. So this is a nonlinear function of the state. This is the product of a matrix times a vector. So this is a vector. This sum is a vector of nonlinear functions of the state. This is the product of a matrix times a vector, which is a nonlinear vector function of the state. But in essence, it's a polynomial in U of degree 2, the same as the order of derivation. So as you can see, this technique or these operators are very nice to apply because you get what you expected. You don't get any surprises. You get just simple expressions in spite of the fact that the nonlinear functions can be difficult to compute in practice because of the dimension, because of the complexity that they have. You can give that to an algebraic manipulator, but internally you know that this type of directional derivative iterated on simple functions like x is just a polynomial of second degree in U. And we will make use of that in order to get the elements of an expansion that we're going to be doing. So the directional derivative operator on vector functions has the same definition for the recursive definition of that J's directional derivative starting from the identity. That's a very simple formula in which the directional derivative along the control vector field iterated a number of J times is just the application of the original directional derivative on the previously found expression of the iteration, starting with the identity for the operation in which no differentiation is carried out, no directional derivative is carried out. So in that manner, we can apply that operator to x a repeated number of times, a finite number of times, and what we're going to obtain is polynomials in U. This is the essence of all this long talk. When you do the iterative operations along the velocity of the state, which is f plus gu, of the elementary function x a number of times, you make that iteration a number of times on the same function x, you obtain polynomials in U of growing order. So if you take J directional derivative of x along the vector field f plus gu, you will obtain a simple polynomial of order J in U. The rest are coefficients, which are vectors accompanying each one of the powers of U, starting from the zeroth power. So that's very easy to remember, very easy to apply. And our intention is to expand the solutions of this differential equation from an initial state, let's say given at the sampling time kt, apply a piecewise constant control to the system and try to get an approximation for the next state or the exact formula for the next state. And for that, we use Taylor series expansion. So the value of the solution of this differential equation, given that U is a piecewise constant control input, given between the sampling time kt and kt plus t, we can expand this in an infinite Taylor series, which will involve the time derivatives of the vector x a finite number of times for each one of the components of the sum all the way up to infinity. And we will particularize this in the value of the initial state. So in essence, since this will be a function of x and u, what we have is the map that will produce us some value of the state after the sampling time in terms of the state at the sampling time kt. And this formula is completely general. And there will not be questions about the convergence because we're dealing with analytic functions. All these analytic functions will have this sort of expression in which the infinite series converges and can be added up. The only problem would be to have a closed form solution of this sum. So our intention now is to actually compute the value of this expansion when small t is equal to capital T and obtain a next state map, in the sense that the knowledge of the state at time t and the control input, which will be hidden here in these derivatives of x, of the vector x, will produce the next state. And when we substitute this x, jth derivative of x by one of these series, or one of these finite sums, we will obtain the influence of the control. This is the reason why we took the trouble of doing this expansion, so that, that we could use it in this Taylor series expansion. And of course, since we'll be involved in all these directional derivatives or Lie derivatives of the vector function x with respect to the control vector field f plus gu, we call that a Lie exponential series. And the Lie exponential series is simply, and this Lie exponentials, sorry, I'm getting some people entering, still entering. Okay, the Taylor series expansion, when we substitute the derivative of the vector x, as a state vector x of jth order, we substitute this by the corresponding directional derivative of the vector x along the control vector field, we can substitute that derivative by this finite sum. So when we do that, we will obtain a Lie exponential series. But it's nothing like, it's nothing more than a Taylor series in which the derivative of x are being substituted by these directional derivatives of the vector function x. So at time kt plus t, we have an infinite sum of polynomials of growing degree, or of growing order in U. So for the, let's say, the fifth element of this series, you will have a fifth order polynomial. For the 10th element of this series, now you have a larger sum of powers of U in a polynomial whose coefficients are functions of x at time kt. So this is an exact formula, but it's a very inconvenient formula because it tells you that you have to sum an infinite series and get all these expressions of these vector functions and see if you can find a nice closed form solution for that formula that allows you to compute the next state at the sampling and the next sampling time in terms of the actual state and the given control input. Even if it is constant, you will require to have powers of that scalar control input accompanying each one of these constituent sums. That might be quite a problem, and you might not be able to identify what all this infinite series gives you in terms of a simple expression in terms of x and u. Sometimes you can, but in general, you won't be able to. It's very difficult to expect that this will give you something nice and simple. So the lesson from here is it is very complex to do exact discretization of nonlinear systems. Even though the structure that we need is still preserved in this expansion, the actual state and the given control input produce the next state in a highly nonlinear fashion. And therefore, the morale there is that it's probably not worthwhile doing it because it's a task in itself to be able to sum all those expressions and find a closed form solution. That's where everything would be worthwhile. If you obtain a closed form solution for that infinite series, then it will be fantastic because now you have a simple formula to plug into your computer and obtain everything. So the most you can do is to be satisfied with an approximation. An approximation of this formula means to take in a finite number of elements in this infinite sum, and that might be questionable for some examples. So, what is the alternative? The alternative is to be satisfied with approximate models of the sample nonlinear system, because in general that series is not reducible to a closed form expression, and to compute a model you just have to confine yourself to a finite number of terms, which might be questionable. So the alternative is to use an approximation, and since the nonlinear system, since we're willing to deal with nonlinear system, the thing would be to have a formula that gives you approximately the value of the next state in terms of the actual state and the control input. And for that, which just might use the Euler's backward or forward formula of the time derivative of the vector function x as a function of time. So that is a common practice, and what it leads to is a nonlinear model of your system in which you have an affine dependence on the control input. This is somehow not sustainable because yes, xkt plus t will be a linear function of u. But the next one will not be a linear function of u. When you take xt plus 2t, this nice structure of affineness in the control input will be destroyed. So you know that, and because you know that, there is no reason in pushing that this is the class of systems we should be dealing with. No, not at all, because this linearity in u is not preserved as you iterate in time the value of the states along the time axis. So what we can do is, in general, to suppose that we have a nonlinear map, which is a function of the state and the control input, independently of the fact that the control input might enter linearly to produce the next state, but that linearity, we know, will not be preserved as time goes on. So for this class of systems, maybe we have to be satisfied with a simple approximation, and this approximation may be good for applications, especially in the lab where you devise your experiments being controlled by a computer. So that's the lesson that we do with all these computations that we did in the previous slides, is that we would prefer something simple for the nonlinear case. And if the system is native, and it's already a nonlinear function of the state and the input to obtain the next state, then we will be able to handle this generality. And we forget about the fact that it might come from a physical system that evolves continuously in time, and that the model is approximate. What we want to deal is with this type of generality, no matter what phi is, whether it's linear or not in the control, it won't make any difference. So this is part of the morale. So before we go to the next topic, is there any questions that you would like to ask? Am I going very fast? Am I going very slowly? I need some feedback.
Yeah, I'm fine with it, Herbert.
You're okay with it? Okay. Hello.
Maybe also
Seems like familiar faces there.
Any input you can. I mean, this is a multi-lecture series, right? So how many lectures are we expecting?
Maybe from now till July, when I leave at in the first week of July, we will have 7 lectures, I guess. 7 or 8 lectures.
Yeah. So we're taking our time.
We can continue when I'm back in Mexico, no problem, because this allows us to do it, this system.
Yeah, so I understand some of these are latest research, right? You did some recent work to complete the picture, so to speak. So
yeah, this is what we were doing in the winter time, and of course this is the formalization of everything we did, but it's been put in the form of lectures so that we can order the material and we can naturally go towards ADRC and flatness and so on.
So some of these are not published?
No, but it is known. It is I mean, my work there, I did it myself, but many of the things that I'm talking about are known.
Okay.
Many of the things are known. They can be found in articles and books. It's not.
But you.
The presentation I'm doing is original, but the work itself. Well, there are some things that I did that you cannot find easily in books, but probably not as complicated as the techniques that people have been using for nonlinear discrete time systems. It tends to be obscured by the difference algebra or the linear differential algebra. All those elements have been used in the past for discrete time nonlinear systems. But here is just an exposition that I wanted to do in order to be able to explain to students what's behind all this and how they can proceed in practice to obtain nice models where they can apply ADRC or apply sliding mode control or apply flatness-based control to nonlinear discrete time systems. This is the idea.
Right. So my understanding, because this is getting late on the other side of the earth, so we can continue and they can watch the video later. But my understanding is, some of these are published or are in the existing literature, and on the ADRC side, there's some recent work. But we're hoping by this series of lectures, we put everything together in one place, right?
Yeah.
So that's what's missing. There's no papers or books. Maybe your book cover part of it, but there's no
very little.
one paper had everything that you talk about in one place. So that's one of the objectives of this lecture, is bring everything together.
You're right. Yeah, that's what we're.
And are you able to share the lecture notes with us?
Oh yes. No problem.
So after the lecture, each lecture, maybe I'll just post it on WeChat or QQ group, the lecture
I'll
notes.
send them to you. I'll be happy to.
Yeah.
Yeah.
That would be great. I mean, people free to go. I mean, free to come, free to go. I know that the lecture, you know, this is 11 o'clock at night in Beijing.
Yes, in many parts of the world, that's true.
So you plan to do another hour or
Half
something
an
like?
hour.
Okay. So we'll do another hour and then we'll do this again a week after. I mean, a week from today, right?
That's true.
Okay.
And a week from today, we can switch to the CSU system. Just it,
Oh, that's okay. It's if you're okay with it, we're fine. It's just CSU system is already paid for.
okay. Yeah, I did pay for this.
Yeah. So
Okay.
other questions from the audience? I mean, this is a more of a introductory lecture that I mean, part of this notational segment, and there's a detailed multi-lecture series on Bilibili that we put the previous lecture course by Professor Cyril Ramirez. We recorded his lectures and we put it on Bilibili, and it's available. So if you are, for the audience, if you're interested on the analog side or continuous time case of this, that lecture has already been given. So this is a more of a parallel material on the discrete side, on discrete time side, and then we're hoping that we're going to learn from Dr. Cyril Ramirez to complete the holistic story on the discrete side. Like he said earlier, that many systems come in the native form of discrete system. It's not converted from analog. So in treatment of sliding mode and ADRC and flatness, there's something fundamentally different. So we're hoping to learn from him. Yeah. So with that, Professor Cyril Ramirez, please continue.
Can I ask a quick question?
Go ahead.
Yes.
Yes, because I'm in China and I'm afraid I possibly will have to go in a few minutes. So maybe you will cover this question in the rest of today's talk, but because I have to go, so I want to ask this question.
Yeah.
So I understand here, you are working on generic nonlinear system and trying to get a discrete version of that nonlinear dynamics. So I have been working on the geometric control. So that's basically on continuous control on Lie groups. But I've been exclusively working on continuous case, and I've never thought about anything in the discrete case. So I'm wondering if there's anything specific for the discretization for continuous dynamics on Lie groups.
In these lectures, no, not really, although they are a beautiful example of discrete time nonlinear systems because they apply to systems that naturally involve manifolds of matrices, things like rotations and so on. They're fantastic examples, but we're sticking to the fundamental issues, the fundamental presentation, in which you can get enough feeling for this so as to be able to apply to simple examples. And the main objective is to drive you slowly towards how can we apply ADRC to models of this sort. So specifically, we will not be dealing with systems evolving on Lie groups. One of the things that derives from this approach that I'm putting here and that I think is worthwhile pursuing is the aspects of homomorphic sequential systems characterized simple homomorphisms evolving in groups. And there are plenty of very nice examples of that in the discrete time case, but they are kind of, out of an introductory course. That's right.
Okay, all right, thanks, got it.
Okay. Well, let's continue for a few minutes just to illustrate the basic notations and the things we're going to be dealing with in our approach to nonlinear discrete time systems. This is the model that we will adhere to from now on. This nonlinear discrete time system constituted by next state map and an output map. So the state will be evolving on a sufficiently large open set of Rn, and the control will be evolving in a sufficiently large open set of the real line. So we are dealing with single input systems. And the outputs, characterized by a nonlinear map H, takes the vectors in the open set X to R. So we're talking about single input, single output systems, which are nonlinear. And the nonlinear map producing the next state is of this form. We will assume that this nonlinear map is sufficiently well behaved. So in order to simplify and not having to write all these two equations every time we mention them, we will refer to this system as a pair. And the pair is the nonlinear next state map and the output map. That's our simplification of all these equations. And it's presumably X is a vector in Rn, evolving or taking values in open sets in Rn, which are sufficiently large. And the controls are scalar controls, and the output are scalar outputs. So phi, the nonlinear function of the next state map, is a collection of nonlinear functions of the state and the input, current state, current input, or given input at time kt. And sometimes we will suppress the dependence on time in order to not to clog the notation too much. For us, the next state map sometimes is placed in terms of x and u. And h maybe will be denoted by h of x. When there is some need for specifying time explicitly, we will do so, but in general, this is the correspondence with what we have. So we have a fairly general nonlinear system. Of course, we have to do some precisions on phi. Phi will be a nonlinear vector function of the state. Some of the elements that we will be needing in the approach is, let's say, the matrix constituted by the gradients of the vector function phi. So the first row is the gradient of the first component of phi. The second row is the gradient with respect to x of the second component of phi, and so on. So this is an n times n matrix. We will have this notation conventionally taking the derivative of this column vector with respect to the row vector x, and we represent that as an n times n matrix constituted by the gradient rows of each of the components of phi. Phi is a vector and u is a scalar, so the partial derivative of phi with respect to u is just a vector in which each component is the partial derivative of the component of phi with respect to u. And h is a scalar function of x, so the gradient of h with respect to x is just this vector function, this row vector of the derivatives of h with respect to each one of the components of x. These three things will pop up very frequently in what we are going to say in the next slides. So it's good to have a reference that lets you know in terms of components what all these partial derivatives mean. As an example, if we had a linear system in which the next state is a linear function of the actual state plus the addition of some influence of the control through a constant vector b, and the output is just the inner product of a vector c times the state vector, is a linear function of the state. If that were the case, then these three elements that we have portrayed here explicitly in terms of the components come up to be, this would be just the matrix A of the linear map. This will be just the column vector B, and this will be just the row vector C transpose. So it just gives you an example on one of the classical examples of linear systems when we deal with such a generality. So in general, we have to think of this as a matrix. We have to think of this as a column vector, and this is a row vector. And they will be frequently appear in the next slides. So the other thing is if we wanted to compute the next output, you see the next output will be a nonlinear function of the next state. So we have to substitute the next state by this nonlinear function of the actual state and the control input. So when you do that, the next output is the composition of the nonlinear output map substituted or evaluated at the nonlinear next state map. So y of k plus 1 will be h of xk plus 1, which is h of 5 of x and u. So this function of functions is a scalar function of a vector function, will be denoted by a composition of maps. So h composed with phi simply means that h is being evaluated in xk plus 1, so that there is actually the expression for the next output yk plus 1, according to our notation. And if we wanted to do something like the gradient of that scalar function with respect to the state, we have to use the chain rule. And since this is a composite function, we will have the gradient of h as a vector, as a row vector, as the first derivative that you will encounter, which is h, which is only a function of x. So we have to take the derivative of h with respect to x. But internally, the h contains a function of x and u. So the next thing would be to derive this vector function with respect to x, and we will get a matrix. So this partial derivative will be the product of a row vector times a matrix. That gives you a row vector again. In the particular case of the linear systems that we are using as an example here, we know by this formula that this is substituted by C transpose and that this is substituted by A. So the gradient of the next output is C transpose A. And of course, since phi is a function of x and u, we can also take a derivative of this composite function with respect to u. And you will have the gradient of h with respect to x, according to the chain rule, times the partial of phi with respect to u. This is the product of a row vector times a column vector. That's a scalar. And in the particular case of linear systems, this will be C transpose times B. This is the first Markov parameter of the linear system. So things which are familiar can be easily recovered within the realm of our generality of nonlinear dynamics and nonlinear output maps. The only thing that we're using here is that this X transpose is necessary to recover all of the linear theory as a particular case of what we're doing. And because otherwise we would run into things like the partial derivative of a column vector with respect to another column vector that is not writable as simply as a matrix. So we prefer this convention of taking the partial derivative with respect to the row vector representing the state. So things like Markov parameters and the elements of controllability and observability matrix will be recoverable from this general notation of calculus in Rn. One of the things we need to assume is a technical condition, and the next state map is going to be assumed to be an analytic function of its arguments x and u. It will satisfy a condition that is called this submersibility condition, or phi is submersive. And what that means is a very simple idea, but it's one that gives us a long way into deriving many of the results. If we compute the rank of this matrix, the partial derivative of the nonlinear next state map with respect to the state, that's a matrix, which in the linear case is just A. And we compute the rank of this A matrix, quote unquote, with this B matrix, which is the partial phi with respect to u. Remember that in the linear case, this came out to be B. The rank of this matrix has to be full rank, full row rank n. You see, this is a matrix which has n rows and n+1 columns. So the maximum determinant that you can obtain from the arrangement of this matrix and this column vector is an n times n matrix. Well, the rank of that composite matrix is going to be n. That condition is a technical condition, and we will explain what it means. It has two important consequences to do this. The first thing is that you gain invertibility of the nonlinear dynamics. If this condition is not put there, then you still will be able to gain invertibility, but at the expense of a lot of operations. And we want to avoid that. The other thing that this has an immediate consequence is some finiteness assumption, in the sense that some of the iterations that we are doing to obtain elements that will serve some purpose in defining structural aspects of the system, those iterations might go on forever. Well, if this condition is enforced, that type of iteration is not necessary, but up to a finite order. This is one of the main consequences of this. Remember, for example, in linear time invariant systems, whether continuous or discrete, you relied enormously on the finite dimensionality of the space, and on the fact that the Cayley-Hamilton theorem allowed you to obtain some kind of recursion up to a finite order. And after that finite order was reached, the next iteration was really a linear combination of previous iterations, and somehow you got stuck into some subspace. Well, if that subspace happened to be the whole space, fine, because you ended up your process right there. You wouldn't obtain anything new by doing some further iterations. Well, the Cayley-Hamilton theorem applies directly because what you're dealing with in the linear case is matrices. But here it's a little bit different, and the Cayley-Hamilton theorem does not apply immediately. So in order to guarantee that finiteness, you have to do an assumption like this. In particular, for instance, the invertibility aspect is that you can have an appropriate partial static state feedback. That means you devise your control as a nonlinear function of the state and of an auxiliary control input. Let's assume you do that. You substitute that into your system, you still obtain a control system pretty much of the same form as the previous one. But this assumption somehow tells you that you know, the local maps in the state and the controls give you a non-empty image in Rn. And so you have an open set as an image. And therefore you will be able, with some luck, to invert the system. So there will exist some feedbacks that allow you to make an inversion of the system. By inversion, we mean that we will be able to obtain previous values of the states by means of inverting this nonlinear map. So for instance, you would be able to obtain xk would be some function of xk minus 1 and vk minus 1. If you wanted to obtain xk minus 1 in terms of xk and vk minus 1, you cannot always do that if phi is any arbitrary nonlinear map, unless some rank condition is imposed. And in order to be able to invert this, you have to be able to at least locally solve for x. So when you map this to a relation between xk and xk minus 1, vk minus 1, there will exist some function that allows you to compute the previous state as a function of the actual state and the previously applied input. That's a very important property, because you cannot always do that in nonlinear maps in general. So generically, we will assume that this is true, because this allows you to use the implicit function theorem in that backwards recursion and obtain the previous value of the state in terms of the actual state and the control that you previously applied. That invertibility is essential because it's not always guaranteed to be satisfied. If you don't do this assumption, this might not be true, that you can compute uniquely your previous states on the basis of the information that you have in the present and in the immediate past. So that submersibility condition is very important. And what it means is that if this matrix does not have full rank, it will be allowed to have at least rank n minus 1, because then you can supply that lack of full rank with the action of B. And when we talk about this vector function, which in the linear case is just the constant vector B, that represents the possibility for feedback. This function is giving us the local idea that feedback will influence locally the whole structure of the system. But the way it influences is to produce a map which somehow is invertible. So either this matrix partial of phi respect to x is full rank, and therefore I have no problem with invertibility, or if it lacks full rank, it can only be allowed to be rank n minus 1, so that this vector might lie in the appropriate subspace, which is not in the span of this matrix, so that it complements nicely the full rank condition, so that you can now be specified as a feedback to influence the state space. That's part of the thing. And what we're saying is that the image of this column vector phi of u, which plays the role of the vector g in nonlinear affine systems, or the vector b in constant linear system, that the image of this phi u is somehow not in the span of the matrix phi of x, if this phi of x is not full rank. If it is full rank, of course, phi of u will be in the rank of phi of x, and therefore there is no problem, because phi of x will also be a function of u in general. So this is the geometric condition. In the linear case, it just tells you a basic formula in which phi of x is simply a, phi of u is simply b. What we are saying with that condition is that the span of A complemented with the image of B always complete the n-dimensional space. So if A is not full rank, B can appropriately complement that full rank, that lack of full rank of A. But of course, necessarily A has to be at most n-1. And that at least n-1, because otherwise, if this is rank n-2, B cannot complement the whole rank to have n linearly independent vectors gathered from the rank of A and B. So this technical condition is very simple to interpret, and it will buy us a lot of nice conditions in order to be able to either invert the system or to invoke a finiteness of the iterations that we have to do to gather the structure of the system. And those iterations don't go all the way up to infinity. They might be constrained to a finite number of iterations. That's what this technical condition does. This condition is somehow hidden in the case of linear time invariant case. And basically because in the approximate discretization of a linear system, the Euler formula will produce a map that's full rank, because you always have the identity matrix in between added to some part of the A matrix. So this is somehow hidden, but in the nonlinear case, it becomes very prominent, because if you don't use this condition, then many of the things that you try to mimic from the linear case will be invalid. And that's the reason why we're doing that. Okay, so with this condition, we will enter into the structure of the nonlinear system, but I would prefer to stop at this point and see if you have any questions, and probably call it off, given that we have 1.5 hours already. Hello, you. How are you doing?
Yeah. So yeah,
Okay.
please feel free to ask questions.
Rafal raised the hand. Okay, Rafal, go ahead. Should I allow you to
Yeah.
I'm here. First of all, thank you very much for this opportunity. This lecture series, but not only this one, but also the one that is already available on YouTube, has been a great source for knowledge, not only to me personally, but to our students at Union University as well.
Thank you. You're very generous.
My question is about not only about this particular lecture, but the lecture series in general. Professor, could you talk about what is the roadmap for this lecture series? Of course, today we are still establishing fundamentals, geometrical theory, differential flatness, and so on. But like informally asking, where are we going with this? Are we trying to establish tools for discretization, or we are trying to explain ADRC in terms of discrete nonlinear systems?
We're trying to establish the conceptual tools that will allow you to understand how to apply things like ADRC in a consistent systematic manner to nonlinear discrete time systems, as opposed to the linear case, which is pretty well known. And our aim will be actually to exploit whatever linearity is hidden in the nonlinear system, so as to be able to define problems in disturbance attenuation, disturbance rejection, ADRC. The nicety that flatness might bring into the picture by dealing with a simplified system that's linear. And what does this mean structurally in the case of sliding mode control, or whatever equivalences there might be between ADRC and those techniques like flatness base or even slide mode control. That's the roadmap. We want to provide you with the conceptual tools that will allow you to be careful in some particular instances in which you have to resort back to the general theory to see if you can apply those tools directly to your particular nonlinear model. And of course, that's the aim. The aim is to disembark in the rich field of active disturbance rejection control for this class of systems.
Thank you very much. Thank you, Professor.
Is that clear, Rafa?
It is. Thank you. That was my suspicion, but I just wanted to make crystal clear. Thank you for being
here. Okay, thank you.
Yeah,
so maybe we have to think about changing the schedule so that people in China and in Eastern Europe can attend these lectures. I don't know.
Can we do it 1 hour earlier, like 9 o'clock?
At 9 o'clock? Okay, that would be like 9 or 10 in China?
Yeah, that'll be 9 p.m. in China.
Okay. Yeah, I have no problem with that.
Okay, so we can, if everyone is okay with that, we can make it 1 hour earlier since there's so many people from China, and so if we can do that, that'll be great.
Okay. Okay.
Yeah. Anyone else has any questions? So this is a chance, and not just this particular lecture. This is more of an introductory lecture, and so hopefully we'll get more into algorithms and applications and examples later on in the lecture series. But the idea is the discrete time system is more and more important with the current focus on Internet of Things on several physical systems. We started this investigation when one of our visiting students, she's here, Haiyan Wang, brought our attention to this problem in industry, where the iteration is not in time but in space, and that was a natural discrete system. There's no continuous counterpart to it. So I think, I don't know if David Wang is still here, but he also brought to our attention, to my attention at least, financial industry. There are issues that can be described only in discrete time case. So after Professor Cyril Ramirez finished the lecture on the continuous slide, differential geometry, and so on, flatness, so we thought maybe it's a good idea to do another one on the discrete time side. So that's from our end.
Yeah. I like this area very much because it leads to a number of examples which are not traditional. I have been looking into several things related to network congestion, and this is a natural environment for those problems. Or as we already did in the winter with production facilities and stock control and things of that sort. There are also beautiful areas that people can I think try, like error correcting codes. They're discrete systems. They evolve in finite fields, but the ideas basically are very, very prone to be used with these techniques. I haven't tried myself, but I suspect that there's a bunch of beautiful examples. Another area is the area of numerical algorithms. Numerical algorithms naturally evolved in discrete time, and they're nonlinear, most of them. So this gives you an opportunity to apply systems theory to numerical algorithms. And much as that, of course, always the case of nonlinear continuous systems, which are approximately described by sample systems. At the end of the day, if you want to implement some of these things in a computer, at least you would resort to the discretization in approximate manner, and this will allow you to give, to confidently go through with the algorithms that you use in continuous time with the discrete counterpart, because there will be a parallel to be established.
Professor, while you were talking, I noticed Dr. Quli Zhi is also here. He just graduated from University of Nebraska Lincoln, and he's working for I think for a company doing motor controls. And he was at CSU attending our ADRC session. And in power electronics, where you have a lot of experiences, the control action is PWM. It's a discrete by nature.
Yeah.
Right. And the feedback is also discrete because you already sampled the system. So the entire plant can be described authentically as a discrete time system. You don't have to worry about the continuous side. The continuous side could be quite complicated, but can we apply this kind of
yes.
Thinking to a motor control or to power electronics control problem, where the problem is described in a native form by discrete notations? Would this make a difference as opposed to doing everything in continuous time and then you digitize the ADRC control algorithm? Can we develop the discrete time version directly from the plant representation?
Yeah, we will be doing that. We will be doing that. In fact, some of the examples ahead, few slides ahead, are
okay.
One of them at least is a boost converter circuit. I have another example somewhere in here in which you have a buck converter attached to a DC motor. And you can see the model there. I don't know if you can see the slide.
No, we can see.
Yeah, this sort of thing is the type of example that would be nice to try in a lab, and I have done so here, and some other models which are also native, is like the chemotherapy and things of that sort. Population models, also some of them can be described easily. And of course, natural nonlinear continuous time systems in sample form, they provide very nice examples. So we will be doing things like that, examples like of this sort, which are nonlinear, and the discrete time version is what you need in order to implement some control strategy. Things of that sort we will be doing during this series of talks, because they are discrete in some sense and very naturally placed in that respect. Yeah, we will have a chance to do things like that.
Yeah, I hope there's quite a few people here are very much experts in power electronics. For example, Professor Li Hui from Shanghai University of Electric Power. He's here, and I think his students are also here. And maybe this could be a example where you can lecture and they can do some experimental validation.
That would be fantastic. That would be nice.
On the approach you present in class, I think that would be direct application, and there has to be something different from what we've been doing. So potentially there are opportunity for new algorithms, for new formulation of problems.
Yeah, I agree.
Yeah. Before I forget, Huyu, can you get the link from Professor Cyril Ramirez and upload the video to the YouTube and the B channel and BD. Okay. I think you muted your microphone. But that's okay. So any other questions? Any?
Okay, great.
Well,
Thank you very much. So we
if
have
there's no other
to.
questions, thank you, Professor Cyril Ramirez, for a wonderful lecture. Thank you for doing this on your own initiative. Thank you very much.
Thank you very much. Thank you very much. It's a pleasure.
Thank you, Professor.
You're welcome. Thank you for attending.
Thank you, Professor.
Bye
Thank
bye.
you very much.
Have a good time and take care of yourselves.
Yeah.
Take care.
Thank you.
Bye.
Bye bye.